Welcome to The Explainer. Today, we are straight up breaking into the digital vault. We're going to uncover the invisible mechanics behind server-side attacks and explore how malicious hackers manage to bypass modern web security. And they do it not by breaking the door down, but by tricking the building into opening it for them. Okay, let's kick this off with a bit of a mind-bending puzzle that forms the very foundation of this digital heist. Ask yourself, how exactly does a hacker log into a highly privileged admin account without actually knowing the password? It sounds like magic, right? Or maybe some crazy flaw in the encryption. But the reality is actually much more elegant. It's just pure exploitable logic. Believe it or not, these few seemingly random characters, the word admin, followed by an apostrophe, a semicolon, and 2 dashes, they are literal lockpicks. An attacker uses them to manipulate an application's underlying logic and bypass the entire security system. But to really grasp how a simple punctuation mark can bring down a firewall, we first need to understand the battlefield where this attack takes place.
Now, we generally divide web vulnerabilities into two main camps. On one side, we've got client-side attacks, like cross-site scripting. These target you, the user, directly inside your web browser. But on the flip side, we have server-side attacks. These threats, which include server-side request forgery, template injections, and our main focus for today, SQL injections, they bypass the browser entirely. They strike straight at the organization's back-end infrastructure. Essentially, they're going right for the vault.
All right, let's zoom back in on our main target for today within that backend, the SQL database. SQL stands for Structured Query Language. It's a highly specific programming language used by servers to manage, access, and modify all that incredibly sensitive info locked away inside a database. And honestly, a massive portion of the modern web still runs on SQL. Usernames, passwords, emails, financial records, it's all managed by these queries.
So, let's look at a concrete baseline example straight from our source material. When you attempt to log into a website normally, the server takes your credentials and generates a standard intended query. It reads, select ID from users, where username equals Vicky and password equals password123. The database simply evaluates this logic. Does this combination exist? If yes, you're in.
But what happens if a hacker decides to use our special lockpick sequence from earlier? Instead of typing a regular name, they inject the string admin : lowercase directly into the post request body right where the username should go. The application, naively assuming this is just a normal name, takes it and passes it directly into the database query.
And right here, this is the heist in action. The injected apostrophe closes the username field early. The semicolon tells the database, hey, this command is ended. And those 2 dashes? Well, in SQL syntax, they denote the start of a comment, which means the database completely ignores the rest of the line. It literally drops the entire password requirement. It alters the logic completely, tricking the system into logging the attacker in as the administrator, simply because the username is admin.
But, hackers rarely just stop at a simple login bypass. Once they're inside, the attack can easily escalate from an authentication bypass to a massive data breach. By injecting a payload using the union operator, an attacker forces the database to combine the results of their malicious query with the legitimate one. This specific command we're looking at can literally spill every single username and password from the target system directly into the attacker's HTTP response.
So the really crucial takeaway here is that SQL injection isn't just about reading hidden data. It is about total system manipulation. Attackers can dramatically expand their arsenal. They can inject an update command which could change every single user's password to password12345, locking everyone out. They could use delete to wipe out critical database records completely. Or they might use insert to secretly create new rogue administrative accounts, guaranteeing them persistent backdoor access to the vault long after they've logged out.
Now, hackers also categorize these threats based on when they actually execute. Everything we've discussed so far, those are first-order injections, where the input is submitted and executed immediately. But second-order injections, they act more like a sleeper agent. The malicious input is submitted and actually stored safely in the database. It just waits patiently inside the system until the application retrieves it and executes it unsafely at some later date.
Think about that exact malicious payload being submitted for a second-order attack. A developer might properly secure their initial sign-up page, so the database just stores this weird-looking username string perfectly safely. But later, when a completely different background process fetches that username, implicitly trusting it because, hey, it came from the server's own internal database, it accidentally triggers the SQL execution. It's a devastating blind spot.
It's almost like a developer trusting their own database a little too much.
But what if the target is completely visually locked down? No error messages, no leaked data on the screen, nothing. Well, attackers can just pivot to blind SQL injections. Instead of getting direct feedback, they infer the database structure indirectly. For example, they might inject a sleep command. If they inject code that basically says, sleep for 10 seconds if the admin password starts with A, and the website takes exactly 10 seconds to load, the attacker instantly knows their guess was correct. It's literally like slowly cracking a safe by listening to the clicks. Okay, so how do we defend against this? Let's flip over to the defense. How do developers lock down the vault? Their absolute primary weapon is prepared statements. This is a brilliant four-step process. First, the server parses the SQL structure. Second, it compiles a rigid statement template. Third, it optimizes the plan. And finally, step 4, and this is where the magic happens, the user's input is inserted. Because the template is already pre-compiled, the server is forced to treat the user's input strictly as plain data, not as executable code. Those malicious lockpicks instantly become completely useless text.
Well, you don't just stop at prepared statements, right? Defenders rely on a layered approach to secure the broader server architecture. They implement strict allow lists, meaning they explicitly define the exact values they will accept, rather than trying to play whack-a-mole guessing every possible malicious input. They carefully sanitize and escape special characters. And crucially, they closely monitor internal network trusts, because they know that if an attacker leverages a different server-side vulnerability, like server-side request forging, they could masquerade as a trusted internal machine and bypass the front door entirely.
So, we've just seen exactly how a tiny little input can crack a massive system wide open, manipulating server-side logic to bypass authentication, exfiltrate data, and seize total control of the vault. I'm going to leave you with this thought to ponder. If a simple punctuation mark can bring down an entire database, what other invisible lockpicks are secretly testing the boundaries of the apps you're using right now? Thanks for joining me for this explainer, and keep your eyes open.